Imagine you're on a cross-country plane trip. The kid next to you says, "Will you play marbles with me?" I mean, I would. Imagine that you're playing marbles, and the marbles, they're doing what marbles do, but all of a sudden they go whoop and roll a certain direction, as if there was a magical force involved. What could explain that? Well, one thing that could explain that is if the airplane was accelerating. If the coordinate system of the airplane was experiencing acceleration, you would see the marbles rolling off in the other direction. An accelerating coordinate system introduces what looks like magical forces. But if the airplane is not accelerating, would it matter how fast the airplane was going? Would that be needed to know how to explain what you're seeing? No, the laws of physics would not change depending on how fast the airplane was going. It would only change if the airplane is accelerating. That is what is meant by an inertial reference frame versus a non-inertial reference frame. A reference frame is a coordinate system. An inertial reference frame is a coordinate system for which the law of inertia, Newton's second law, works. An inertial reference frame, the law of inertia works. It's not accelerating. A non-inertial reference frame means that the coordinate system must be accelerating because we are not able to use the law of inertia anymore unless we fix it with some magical forces like the centrifugal force. It's a magical force we have to add in to try to fix the law of inertia. Einstein's theory of relativity has two postulates, and the first is that the laws of physics are the same in every inertial reference frame. Makes sense. The second is that the speed of light is the same in every reference frame. Okay, well, let's unpack those two postulates, adding math that's no more complicated than the Pythagorean theorem, and you will actually understand the theory of relativity. It sounds like it's all space and time travel, and maybe it's beyond your grasp, but actually it's well within your grasp. The math is very simple, actually, and you just need to take those two postulates plus some simple math, and let's unpack what it means together. And that starts by digging into your reading. Imagine Grover is riding on a train marked A. The train is going to move in the positive direction as measured by B, the ground. There's two different coordinate systems to describe Grover's motion. In the coordinate system of the train, Grover's not moving, but on the ground, Grover is moving in the positive direction. Now the train stops and moves around. Grover has a velocity as measured by the ground in the negative direction. Now Grover has roller skates, and he is going to move on the train while the train is stationary. The train is still stationary, Grover's going to move back. In this case, Grover also has a velocity as measured by the ground in the forward and the rear direction. But what about when both the train is moving and Grover's moving with respect to the train? We could describe his motion with respect to the ground by combining his motion as measured by the train and the motion of the train as measured by the ground. That is called a Galilean transformation. And the math actually is not so difficult. It looks a little intimidating at first, but give it a try. And let me just introduce to you what the notation means. Well, there's two different rulers here, and we're going to label them differently. It's up to us. Neither one of them is special, but what's on the ground, let's measure what's called A here. Let's call that x prime, just to connect with what the way your book describes this. And let's measure this ruler on the ground, which is marked B. I'm going to call that position X. And position X is measured by observer S. Position X prime is measured by an observer, let's call it S prime. And it's an observer that's traveling with the train. When Grover's on roller skates and he is going in the positive direction as measured by the train, and the train is moving in the positive direction as measured by the ground, can you describe to me Grover's position as measured by the ground is going to be Grover's position as measured by the train plus what? Plus how far the train has moved as measured by the ground. Does that make sense? Let's play that video again. Here comes Grover. Grover's displacement is in the positive direction, we're going to add to that displacement how far the train has gone. Let's describe this in terms of velocity. That might make more sense. If Grover is moving forward, as measured by the train, with a velocity we'll call u prime. Now u is going to be reserved for the velocity of a thing, and v for the velocity of a coordinate system. We're describing the velocity of the train as measured by the ground as v. V is the velocity of the train, not Grover. But the velocity of Grover, we're going to call u, and u prime means the velocity of Grover as measured by the train, right? But what's the velocity of Grover as measured by the ground? Is it larger or smaller? I have to add to the velocity of Grover as measured by the train what quantity to get the velocity of Grover as measured by the ground? What is the quantity? I have to add to Grover's velocity the velocity of the train with respect to the ground. Now, what about when the train stops and turns around? V would be negative. Does that make sense? I would take Grover's velocity, which is in the negative direction, as measured by the train. So this would be negative, that would be negative, and I would get a very negative velocity for Grover. What about when the train is moving forward, but Grover is moving backwards on the train? What's going to happen there? When the velocity of Grover as measured by the train is in one direction, but the velocity of the train as measured by the ground is in the other direction, u plus v are equal and opposite. Let's illustrate. They add to 0. U would be 0 in both of these cases. Okay, so give this a try. This is within your grasp, and ask me whatever questions you have. We'll pick them up in class and then work towards the surprising implications of this simple math. I'll see you in class. This year I had a goal for my university physics class to record a really short chapter trailer for each chapter to help ease my students into the discipline of reading their textbooks. It's a difficult thing to do, and it's something that's important for their futures. But there's just one problem with that. I can do 1 or 2, but doing it for every chapter, well, that's a different story. So instead, I've invested a little time on the front end in a live production setup using OBS Studio. I can switch between these different scenes that I set them up once, and then when I'm done, I've got all the production that's going to happen. I mean, whatever I do live, that's what's going to ship, because that's the reality. I've got too many things to do, papers to grade. And so this was my first attempt to do that from my home studio, where I don't really have ideal lighting. I've just got a yellow wall behind me that I'm using as a chroma key background. And I loaded up a video in VLC. I can play it and stop it. I can draw on it. This was coordinate x prime as measured by observer s prime, and the other coordinate was for the ground below was x as measured by observer s. I'm drawing on my iPad, and so what you're seeing here is my webcam plus my iPad, which for my iPad white is transparent, and for my webcam the yellow wall behind me is transparent. And then I'm adding a VLC source or any other source so I can draw on it. Because sometimes, I also like to put a figure here or something like that. There's all these complicated figures in the textbooks, and sometimes it helps to talk through it with my hands. So if you'd like to see more things like this, hit subscribe and let me know what else you'd like to see. I'm not a professional YouTuber. I'm a teacher, and I've got children to take care of. Actually, it's lunchtime right now. So